by defining what a rational function is. And so you can see written here at the top of the page, this is something that we could write in the form f of x equals p of x divided by q of x. And in this fraction, we are going to have both p of x and q of x represent polynomials. And so what's special about these rational functions are that there could be an x down here in the denominator. And so what we're looking at here in this first problem is a really simple example of a rational function. It's just 1 over x. When we have that x down in the denominator, we want to be really careful in thinking about the domain of that function. We know that the domain is describing what are the possible inputs that can go into that function. Well, the reason we need to be careful here with a fraction is that we can never have a denominator of 0. That is not allowed. It is undefined. You would get an error in your calculator if you tried to do like something divided by 0. It's just something that we cannot do. And so for this particular example, we would say that the domain is all real numbers except x cannot be 0. So there's a little note here that our domain is always going to exclude any x value that could make the denominator 0. Looking at this really simple equation here, 1 over x, we are going to make a table of values to help us start to see and figure out what the graph is going to look like. And so we have some negative x values here that we're going to plug in. We've got some positive x values. We have a few fraction values. Let's just start here at the beginning of our table. So with x is negative 3, we're doing 1 over negative 3. Well, that's just going to turn it into the fraction negative 1/3. A positive divided by a negative equals a negative, so you could think about just having like a single negative out in front of that 1/3 fraction. Then we have 1 divided by negative 2, that would be negative 1/2. 1 divided by negative 1 is negative 1. Now notice the next value we have here is negative 0.5. We're going to come back to that one in just a moment, so we're going to skip it. We're going to actually continue here with the 0. So notice how if we were to plug in 0 for x, we would get 1 divided by 0, but we can't do that. So that's the exact situation that we were just talking about that makes it undefined. It's not allowed. And so in this position in the table here, I'm just going to write a UND that stands for undefined. In other words, there's no value of y that is possible if x is equal to 0. Okay, now let's take a look at some of these positive values here. So we are going to do this positive 0.5. And I want to use a little bit of space here at the top to write this out. So if we think about what's going on with the numbers, this 1 divided by 0.5, I could rewrite this out horizontally with like a more traditional division symbol. One way to interpret the meaning of this problem is think about it asking how many times does 0.5 fit inside of 1? How many times would that be? 2 times. There's 2 halves that fit inside of 1. And so this result ends up being 2. You can check it on a calculator, but I think it's kind of nice to see and think about how the numbers work together. So 1 divided by 0.5 is 2. The next. Yep, so going back to this negative 0.5, positive divided by a negative is just a negative. So that'll be negative 2. Okay, and then when we take a look at the positive values here, we have 1 divided by 1, that's 1. 1 divided by 2, we're just going to write that as 1/2. 1 divided by 3 is 1/3. Okay, so we're going to go over here to our graph, and we're going to start to plot these points. So what we should see here is that this table is really just giving us ordered pairs that are going to be on the graph of 1 over x. So if we start with the first ordered pair here, we have an x value of negative 3. Our y value is negative 1/3. So it's just going to be about 1/3 of the way down. So it's going to be somewhere right about here. All right, then when x is -2, we have a y value of -0.5. So it's a little bit further down. It's still only half a square down. Then we have the point -1, -1. Now, let's think about this next one. When x is -0.5, it's going to be right about here. And then that's going all the way down here to -2. Okay, then we're going to skip over the position where that y-axis is. The y-axis is when x is equal to 0. And we saw here that that was undefined. In other words, this graph will not have a y-intercept. That is not possible for us to have a y value when x is 0. So we're going to skip over that. But when we go over here to where our positive x values are, we have when x is +0.5, our y value is 2. And then we have the point 1, 1. And then when x is 2, y is +0.5. So that'll be right about here. And then when x is 3, we have that y is +1/3. All right, so it's kind of creating a little bit of a curved shape with what we can see so far. Let's think about what would happen here if we continued further to the right. So like how we saw that when x is 3, the y value is 1/3. Well, when x is 4, the y value would be 1/4. So like it's a little closer to the x-axis. When x is 5, the y value would be 1/5. That's a little closer to the x-axis. It's a little closer to 0. And that's going to continue on and on. So if you think about like if x is 100, the y value would be 1 divided by 100, which is a number that's really, really small. And so it's going to get closer and closer to the x-axis. It's getting closer and closer to the y value of 0, the further that line moves to the right. And so what this creates is a horizontal asymptote, kind of similar to what we just had with our exponential functions. It's a value that is just approaching. It's kind of like a magnet that's like pulling the curve closer and closer. I always like to show the asymptotes with a dotted line. But if it's right on top of the x-axis, I do mine a little bit slanted. I have mine here in red so that it sticks out to us a little better. Now, on the left-hand side here of our graph, a similar thing is going to happen here. So let's go ahead and connect these points. As those x values get smaller, as they get more and more negative, this curved part, again, is going to get closer and closer to 0, closer to the x-axis. It's going to be very flat on the other side as well. All right, so let's make a little note here that we have a horizontal asymptote. It's right on top of the x-axis, and so the equation for that is y equals 0. Anytime we want to do a horizontal line, it needs to be in the form of y equals a number, and that number is just the y value where that horizontal line is sitting. All right, so let's talk about what happens here in like the middle part of our graph. So we have our points connected a little bit on the inside. If we think about what we just did here, like that 1 divided by 1/2 is 2, let's think about another x value. So if we had an x value that was even a little bit closer to the y-axis, like maybe the x value of 1/3 would be right about here. Well, if we did 1 divided by 1/3, that would be asking how many times does 1/3 fit inside of 1? How many times would that be? This would be 3 times. All right, so if x is 1/3, the y value, notice how it's getting higher. Now it's a y value of 3. If x was 1/4, if it was even closer to the y-axis, 1 divided by 1/4 would be 4. So it's getting higher, but it's getting even closer to the y-axis. And that's going to actually continue forever as this line goes upward. And the same exact thing is going to happen down here below. So as it's going up or as it's going down, it's getting closer and closer to the y-axis, but it's not going to actually touch or cross over. So this one also has a vertical asymptote. And yes, that is the equation x equals 0. In our case, it's right on top of the y-axis. And we know that to make a vertical line, it always needs to be in the form of x equal to a number. So this right here, talking about the asymptotes and where they are, that's going to be our focus for the rest of our time today, is just to figure out, like, how can we identify from the equation, we have a lot of different equations that we're going to look at, what type of asymptotes it has and where those asymptotes are. So when you're ready, let's go ahead and turn over to the next slide, and we're going to dive a little bit deeper into the vertical asymptote situation. And we're going to start by just looking at some bullet points here at the top of the page. So these are some characteristics, just some things to know about the vertical asymptote. First off, the graph cannot ever cross through a vertical asymptote. So the graph could have one vertical asymptote, or it could have several, and they occur at x values where the function is undefined. We just saw this on our first graph, where the function was undefined. That was for the x value of 0, and that's the x value where the vertical asymptote is passing through. And so because of that, it's very simple to find them. We just need to figure out what value of x could make our denominator 0. And so to find it, we're going to set the denominator equal to 0 and solve for x. All right, so we have our first equation here. This is actually the same one that we graphed already on the front side, so it should look familiar. We're just focusing on the denominator part here. Now notice if we go ahead and set that equal to 0, we don't actually have any extra steps that we need to do to solve for x. It's just already done for us. X equals 0. Sure enough, we saw that was the equation for our vertical asymptote on the first page. All right, let's see how this next one will go. Now we have a little bit more happening on our denominator. So we have x minus 3. When we set that equal to 0, let's think about adding 3 to both sides. This one has a vertical asymptote through a line x equals 3. Now, if you think about this, going back into our equation, if x is 3, and you were to plug 3 in for x down here, you have 3 minus 3, and that would equal 0. So that's why it's a problem, is that when you plug it in, it makes the denominator 0. All right, let's look at the next piece here. So we actually have two parts in the parentheses. I'm going to highlight them so we can see them separately. When we think about setting this whole denominator equal to 0, because these two parts are multiplying together, either the first one could be 0 or the second one could be 0. So this is actually going to give us two different vertical asymptotes. And so we're just going to do the work for each one. So we have x plus 4 equals 0, or x minus 2 could be 0. And that's going to give us vertical asymptotes of negative 4 and positive 2. All right, now sometimes in order to find the vertical asymptote, we have to factor our denominator first. And so that's what we're going to have to do in these next three problems. Our goal with the factoring is to turn it into something that looks like this. So it's very easy to do when you have it with the two parentheses side by side. We need to get this into the form that has the parentheses. There's some different factoring strategies that we'll see, all things that we've done before, so it'll be a little bit of a review. The first one here, the x squared minus 64, this is a difference of squares. And so x squared, also 64, those are perfect square numbers, and they're being subtracted. So with our difference of squares, it always factors into two parentheses side by side. We always have one plus sign and one minus sign. Then all we're really doing is we're just taking the square root of the first term. In this case, the square root of x squared is x, and we're listing it first in the parentheses. And then we're going to take the square root of the second term. So in this case, we're just taking the square root of 64, which is 8, and that 8 is listed second. So it's really x plus 8, x minus 8. The reason that we have to have the plus sign and the minus sign is so that when you FOIL this out, the positive 8x is going to cancel out with a negative 8x. And so that's why it's just x squared minus 64. All right, so when we have this factored, and we set this equal to 0, let's notice again here that there's really two parts to this. So either x plus 8 could be 0, or x minus 8 could be 0. I'm going to set each one equal to 0 separately and solve, and we're going to get two vertical asymptotes. So we have one at negative 8, we've got another one at positive 8. All right, let's take a look at our next one here. So in our denominator, x squared minus 10x, well, this is not a difference of squares. So 10x is not a perfectly squared term. It's also not a trinomial. We only have two terms here. And so really the only other option we have in terms of factoring is to think about the greatest common factor. So in other words, what is the biggest thing that both of our terms can be divided by? And in this case, it looks like the only thing they have in common here would just be a single x. And so if we divide an x out of each part, in parentheses here, that's just going to leave us with x minus 10. All right, we're still going to think about this as two separate pieces being multiplied together here. Since they both involve an x, it's going to lead us to two different vertical asymptotes. And so the first one is actually already done for us. We don't have to solve. It's just x equals 0. And then the next one here would turn into x equals positive 10. So if you think about x minus 10 equals 0, add 10 to both sides. It's also kind of just like switching to the opposite sign of the number that you had inside of the parentheses. Now let me just make a quick note here, because you're going to see something like this on the homework assignment. Let's say when you factored out your greatest common factor, you have something else out in front. Like let's say that you also had like a 2 that was out in front. So maybe it was a 2x that you divided out of everything. Well, that 2, because it's not an x, it's not a variable, you can actually ignore that when we're solving these. If you think about this part here, if you get 2x equals 0 and solve for x, we'll divide both sides by 2. 0 divided by 2 is still 0. So really you can ignore that. If there happens to be another number in front, it's not going to affect what your vertical asymptotes are. All right, let's take a look then at this last one. So now we do have a trinomial. It is a basic trinomial because it's just a positive 1 in front of the x squared. So we are going to be able to factor it into two parentheses side by side. And here we're just going to figure out what multiplies to negative 15 and adds to positive 2. So it looks like we will be able to do like positive 5 and negative 3. So those special numbers first, those are not the vertical asymptotes. That's just how we are going to get this factored, so we get our parentheses filled in. Then we're going to set the whole thing equal to 0. I'm going to use my colors here so that we can see that there's two different parts to this. So we're going to get two answers for our vertical asymptote. So we are going to get negative 5 and positive 3. All right, now the problems down below are going to be showing us a unique situation, kind of a special case when it comes to thinking about finding vertical asymptotes. Let's try to show this here in our very first equation. If we try to think about factoring our denominator, so the same thing that we just did, the x squared minus 25, that is a difference of squares. So we can factor that into x plus 5 times x minus 5. But here's something I want you to notice here. If we were to put parentheses around that numerator, x plus 5, notice that we have an x plus 5 on the numerator, and we also have an x plus 5 on the denominator. They can actually cancel one another out, giving us a more simplified form of our equation. On the numerator, all we're left with is just a 1, and then on the denominator, we're left with x minus 5. So here's how we can move forward with this. To get our vertical asymptote, I'm going to use a VA to represent vertical asymptote. We are going to be looking at whatever is in the denominator in the simplified form. So we canceled out. Whatever is still left is going to correspond to a vertical asymptote. I'm going to change it to the opposite side there because I'm thinking about doing x minus 5 equals 0, solve for x. So we have a vertical asymptote at positive 5. However, let's still talk about the x value of negative 5. Because x cannot be negative 5. If you were to put a negative 5 up here in the original equation, like negative 5 squared is 25. 25 minus 25 is 0. So x still cannot be negative 5, but because it was from the factors here that cancel, it's not enough to be a vertical asymptote. Instead, the way that it's going to show up on the graph is it's going to be a hole. So here's how we're going to write this. We're going to say we have a hole at the x value of negative 5. And that hole came from the part that canceled. All right, so let me actually show you down here below, like what this might look like. So we can wrap our mind around a graph that has a vertical asymptote and then somewhere else it has a hole within the curved part of the line. So imagine that we have a rational function. So let's go ahead and mark out where the vertical asymptote would be. So it's going to go through the x value of positive 5. And then let's go ahead and mark out 1, 2, 3, 4, 5. That's where we have an x value of negative 5. Okay, so the graph of this one would look something like this. So our line is moving along, and when it gets to the x value of negative 5, now it's a hole, but then it's just going to keep moving on after that. So maybe that's what like the left-hand side of our graph looks like. The right-hand side might look something like this. What this graph is, this is actually transformed from the 1 over x that we did on the front page. It's just a transformation. So the x minus 5 down here in the denominator means that the original graph is now shifted 5 spaces over to the right. So that's where we kind of get this general shape. But then we just make a big hole when we're actually graphing it, if we have a hole. Okay, so there's a fill in the blank at the very top of this section here that we're going to go ahead and fill in now. We're going to fill it in with the word hole. So let's read the sentence. It says, any factor in the denominator that is also a factor in the numerator, meaning we had an x plus 5 in both the top and the bottom, that is going to result in a hole in the graph. All right, so I'm going to give you a couple minutes here. I want you guys to go ahead and try the next 2 problems. So think about all that we have talked about so far, and let's be very clear in how we are representing our answers using symbols here, like is it a vertical asymptote or is it a hole, and what are the locations of those? So let's take a look at this one here in the middle. So hopefully you saw that we can factor our denominator here. This is just a basic trinomial. So we're going to factor it into x plus 7 multiplied by x minus 3. And then notice that we had an x plus 7 on the numerator. All right, so because that was the same as this x plus 7 down here on the denominator, we can cancel those. And because we're canceling it, the x value corresponding to that part that would make the denominator 0, so if you did like x plus 7 equals 0, then x would be negative 7, that's going to correspond to a whole. I'm just going to say here that we have a whole at the x value of negative 7. So it's part of our answer. Then we're going to look at the part of the denominator that was left. So in the simplified form, the only thing we're left with is this x minus 3. That's going to correspond to a vertical asymptote, just like it did at the beginning of our paper. So we have a vertical asymptote at x equals 3. All right, then we have something really interesting happening in the third problem. So notice how on this one, it's not the denominator that can be factored, it's actually the numerator that we can factor. So the numerator is a difference of squares, so that's going to factor into x plus 3 times x minus 3. And then on this one, we also had an x plus 3 in the bottom. And so that's going to be able to cancel out with the x plus 3 on the top. And so the simplified form of this is not a rational function anymore. It's just y equals x minus 3. And that's actually just the equation for a regular line. There's not going to be a vertical asymptote on this one because in the simplified form, we don't have a denominator anymore. We don't even have a possibility for the denominator to be 0. But we do have a whole, and it's going to correspond to the x value that would have made the denominator 0 for the part that we canceled. So we have a whole at negative 3. Now, let me just show you here on this one what that would look like. So if you think about x minus 3, well, that's just a regular straight line. It has a y-intercept at negative 3. It's got a slope of positive 1. And we just have a whole at the x value of negative 3. So imagine that our line is just going upward like that. On this side, as soon as it gets to the x value of negative 3, now there's a hole. And then it's just going to keep on going after that. So that was kind of an interesting thing that happened there. All right, so those are our vertical asymptotes. We're going to continue now over on the next side, and we're going to take a look at horizontal asymptotes. All right, so with our horizontal asymptotes, we're going to start again by just looking at some of the features, the characteristics at the top of the page. So here's the thing about horizontal asymptotes. Really what they do is they're describing the end behavior of our rational function graph, meaning it's telling us what the y values are getting closer to as the x values get really, really big on the far right-hand side of our graph, and as the x values get really, really small on the far left-hand side of our graph. So if I were to just copy like a quick sketch of the graph that we did on the very front page, remember that the horizontal asymptote was at y equals 0, so it was right on top of the x-axis, and our curve looks like this. So what we mean by the end behavior for a rational graph is like on the far left end, the y values there are getting really close to 0, and on the far right end, the y values are also getting really close to 0. So that's why that's our horizontal asymptote. Notice how the horizontal asymptote really does not tell us anything about what's happening on the inside part of our graph. It's really just giving us information for those ends. The thing about horizontal asymptotes is that the graph can actually cross through a horizontal asymptote. It doesn't have to, but let me show you another picture here of like another kind of common possible thing that could happen. Could be having a horizontal asymptote at y equals 0. It's possible that it could be something that has two vertical asymptotes. So maybe we have like one on either side. And our curve might look something like this. So on the outside piece, On the two ends, it might look something like that. In the middle, it's possible that it could go like this and just completely cut through the horizontal asymptote. Well, that's okay, because notice how on this one, it's still giving us information about the end behavior. On the far left, it's getting closer to that asymptote, and on the far right, it's getting closer to the asymptote, but it is possible for it to cross through. You would never cross through a vertical asymptote because it makes your function undefined. Like you could never have an x value that makes the denominator 0, but the horizontal asymptote behaves a little differently. Also, the graph can only have one horizontal asymptote. All right, and here's how we find them. They depend on the degree of the numerator and the degree of the denominator. So remember back from chapter 5, when we first learned about polynomials, we saw that degree is just the highest exponent of the polynomial. And so on this numerator part here, we're going to pretend like it's like a times x to the n. There may or may not be other terms behind it, but let's say that this n is the highest exponent on the numerator. So we're going to say that the numerator has a degree of n. And then on the denominator here, we have this b times x to the m. So let's say that the m here is the highest exponent on the denominator. So we'll say that the denominator degree is m. There are three ways that the two degrees can compare to each other. So one possibility is that the degree on the top is less than the degree on the bottom. And so here's an example of what that would look like. So if you look at the degree on the top, the highest exponent we have here, that's a degree of 2. And then notice down here on the bottom, that's a degree of 3. So we're just looking at the exponents here. We have a nickname for this situation. We call this one bottom heavy because it has a bigger exponent, a bigger degree on the bottom. If it's bottom heavy, no matter what the actual equation is, if it's in that category, your horizontal asymptote is always going to be y equals 0. That is this line right here, right on top of the x-axis. It's the same horizontal asymptote that our first graph had today. All right, let's look at another situation here. So another possibility is that it's the same degree. So if the degree is the same on the top and bottom, here's an example. So this one has a degree of 2 on the top, and it has a degree of 2 on the bottom. If the degree is the same, what we're going to be looking at is the ratio of the leading coefficients, the numbers that are out in front. So in this case, it would be y equals 3 over 1, which just simplifies down to be 3. To make this a little bit more general, we're going to use a over b to connect it back to what we said up here. A is just whatever's in front on the numerator, and then b is the number we have in front on the denominator. So it's like a over b. For our example, down here below, it would be 3 over 1, which is really just the same thing as 3. All right, and then the only other situation we have is if the degree on the numerator is bigger than the degree of the denominator. So notice how in this example here we have a degree of 3 on the top, but we only have a degree of 2 on the bottom. So this one has a nickname. We call it top heavy. And this one is pretty simple to deal with because all you have to say is there is no horizontal asymptote. Or you can just say none. All right, so there are some problems right down below this that I'm going to have you try. So there's 8 new equations there, and you're going to think about what situation it is Is it bottom heavy? Is it same degree? Or is it top heavy? And then you are going to write the equation for the horizontal asymptote, if there is one. I'm going to take a couple minutes to work through all of them, see how you did. All right, so on the first one here, so this one is technically bottom heavy because it's a degree of 2 on the bottom. Technically, this is a degree of 0 on the top. So if you do not see an x at all, it's really like x to the 0. But remember, anything to the 0 is 1. So that's why we don't show the x at all. So this one is bottom heavy. On the next one here, it's a degree of 1 on the top and it's a degree of 1 on the bottom. So it's the same degree, so it's going to be y equals 3 over 1, meaning that 1 in front of the x on the bottom, but that really just simplifies to be 3. All right, we have the same degree again on this one, so it's y equals 4 over 16, but you could simplify that down to be 1 over. All right, then we have top heavy. So 3 on the top is a bigger degree than the 2 on the bottom. We do not have a horizontal asymptote. Down here on the bottom here, we've got the same degree. So it's y equals 5 over 10, or you can write it as y equals 1/2. Then we have bottom heavy next, so that's y equals 0. Then we have a top heavy. We don't have one. And then finishing out here, we have another one that's bottom heavy, so it's y equals 0. You do need to know these 3 situations. So as you're starting to go through and practice these, you want to think about kind of quizzing yourself and make sure you know what the 3 categories represent.